Hi friends, in the last video we learned in this chapter thermal phenomena, that is relation between the gamma P and gamma V for a gas. In the last video we learned up to this. Now we are going to learn how much amount of heat will flow from the one body to the another, or one part of the body to the another part, and on which factor it depends. Actually, like all other forms of energy, heat is a form of energy. That's why heat flows only when there are two conditions. The first condition is there must be a temperature difference between the two bodies, or two surfaces, between the two surfaces of a body. There must be a temperature difference, otherwise the heat will not flow. Okay, the first condition. Second condition, either the two bodies directly in contact or indirectly in contact through a medium. Okay, so these are the basic two conditions due to which the heat flows. If they are not maintained, then heat will not flow at all. So, like all other forms of energy, this is the condition. Let us consider here the condition is maintained, strictly maintained here. Now, the solid is considered here, but the temperature of the two faces of the solid are not same. Now, this is the A, B, C, D, one face of the solid, and this is E, F, G, H. E, F, G, H. The temperature of this phase, let the temperature be temperature T1, and the temperature of the EFGH, that is the temperature is the T2. Temperature is T2, and here the temperature is T1. And the distance between the two surfaces, let this is be the distance, let this is be D. D be the distance between the small d, that is the thickness. We can assume this, that is the width or thickness, or the distance between the two opposite faces of the solid, that is D. If there is a temperature difference, that is T1 not equal T2, then there is a possibility of transfer or flow of heat from one surface to the another. Now we consider that, and we consider here that T1 greater than T2. T1 greater than T2, so heat will flow from this surface to this surface. Heat will flow from this surface to this surface. The surface area, let the surface area, the area be, let this is the area be capital A. Capital A is the area of the surface. Okay. Then how much amount of heat will flow? Just see here. Let the amount of heat flow, amount of heat flow we represent this, that is the amount Q. Q be the amount of heat flow from the ABCD to the EFGH surface. This heat flow Q directly proportional with the surface area. When the surface area increases, the amount of heat flow from one surface to the another also increases. This Q also increases if the temperature difference increases, that is T1 minus T2. When the temperature difference rises between the two surfaces, then also the more amount of heat will flow from one surface to the another, ABCD to the EFGH. Next, if the time of flow increases, time of flow of heat, that is time T. T is the small t is the time here. Small t is the time. To remove the confusion between the temperature and the time, we can represent this temperature by using theta 1 and this temperature by using theta 2. In generally, we represent T for temperature but here time is another one factor. That's why we can represent this by theta 1, and theta 2 is the temperature difference between the two surfaces. So we can write this as theta 1 and theta 2. Okay, now so this will be theta 1 and theta 2, theta 1 and theta 2. So t is the time here, time of flow, time of flow of heat. When the time increases, the amount of more heat will flow from one surface to the another. Number 4, let's consider when heat flows from one surface to the another, if the distance increases, the heat will lose during the flow of heat. So when distance decreases, more heat will flow. When the distance increases, less heat will flow. So the amount of heat flow, of course, it is inversely proportional with the distance d. Inversely proportional with the distance d. Another one factor is also here. Another one factor, that is the nature of the material. If it is made by a good conductor, more heat will flow. If it is made by a bad conductor, less amount of heat flow. Though there will be large temperature difference, if it is made by insulator or bad conductor, less heat will flow. Okay, so this is the nature of the material. This is the number 5, nature of the material. Nature of the material. This is the rectilinear flow of heat through the solid, and these are the factors on which the amount of heat flow depend. These are the factors on which the amount of heat flow through the solid one surface to the another depend. Mathematically, we can write these 4 factors very easily. That is Q proportional A into theta 1 minus theta 2 into T divided by D. This is the mathematical representation by introducing a proportional constant, that is Q equal constant K, proportional constant, into A into theta 1 minus theta 2 into T by D. This is the standard relation. Here K is called, here K is the proportional constant. Proportional constant, and this is called, this K is called thermal conductivity. This is called thermal conductivity of the material. Thermal conductivity of the material. Okay, we can define this. We can define this by using this relation, that is Q equal K into A into theta 1 minus theta 2 by theta 1 minus theta 2 into T by T. From this relation, the K equal Q into let's see here, into D divided by A into theta 1 minus theta 2 into T. We can define this K, thermal conductivity of the material, very easily, because there is a standard rule to define a physical quantity or a constant involving some other physical quantities. First we have to make the denominator 1. So if A equal 1, that means per unit area of cross section, and theta 1 minus theta 2, this is equal 1, unit temperature difference, T equal 1 in unit time, and D equal 1, and D equal 1. Then what happened? From this relation we can write this K, the thermal conductivity of the material, will be the amount of heat flow in unit area of cross section through unit temperature difference in 1 second. So this will be the thermal conductivity of the material. Okay, and from this we can easily find out the unit of thermal conductivity. That is the unit of K. K is the thermal conductivity. In SI unit, just represent the unit. That is the Q is the unit of heat, that is joule, into distance meter divided by area, that will be the meter square, into temperature Kelvin, that is Kelvin K, into second. That is meter and meter square cancel each other. Only the remaining part will be joule per meter. Kelvin, joule per second. This is equal watt. Watt, meter inverse, Kelvin inverse. Similarly, in CGS unit also we can write this, that is calorie is the CGS unit of heat, and calorie second inverse, centimeter inverse, and degree centigrade inverse. But this is very important. The SI unit of the thermal conductivity, very important. Each and every year you can see this in your board exam question paper, Madhyamik question paper. You can see this in MCQ or in short question, either in group A or in group B. What will be the SI unit of the thermal conductivity? Okay, today up to this.